All right, welcome back to the afternoon session of our 11th day of the Advanced LLM Bootcamp. The topic now is diffusion models as generative models. Now, we are going to cover 2 or 3 papers, but I'm not going to go literally line by line over the paper. Diffusion models have become quite dominant. So unless you have just come back from a multi-year retreat in the mountains, you have probably known about diffusion models and played with them. So can I assume that we all know what diffusion models are, what stable diffusion is, what Midjourney, all of those things are, DALL-E 2 is, and so forth. So there is a bit of history to it. When people try to go from image to text, the first efforts that you see, successful or rather big milestone efforts, were that of CLIP. Remember, contrastive learning. So given an image, given its caption that you scrape off the web, now you can create a joint embedding. And when you do the joint embedding, you take the image, you pass it through a VIT, you take the text, pass it through again to an encoder, and what you end up with is 2 vectors, and then you use contrastive learning. In other words, and let me just bring it up, because a clip will be relevant to what we are going to discuss now, right now. Yeah, so anybody would like to, instead of me summarizing it, anybody would like to summarize the gist of CLIP? By now, it should be, we have gone over it so many times. So you have an image. Here's a cat. Okay. And then cat sleeping on the couch. Let's say, is the caption. This is your text. This is your image. The image part, you can pass it through a VIT style, VIT, swim, whatever, or image encoder. And what do you get? You get a vector, which is the image vector, isn't it? You can pass the text through an encoder too, text encoder. Think word like. And you get what? A text vector, isn't it? Now, contrastive learning. Now, what do? You try to create a space in which VI, VT, in simple logical terms, the distance is minimized, but the distance between D, VI, and a random text. So you can take gibberish, some random text, if you want to get random. You want to make sure that this distance is maximized. That is your classic contrastive learning, isn't it? A contrastive loss function learning. At the end of it, what it does is you end up with a vector space at which, irrespective of whether it's an image or it's a text, V image and V text, they're close to each other, so V random is far away. This is a very successful and multimodal encoder, isn't it? Are we together, guys? And you have a multimodal encoder. So therefore, we have ways. Now the evolution of CLIP was, and this is the CLIP, the evolution from CLIP was to blip to then language models came in. It came to Lava, and we have been doing all of that. We won't rehash that territory anymore. But suffice is to say that we can go from text, from image from image to textual description of the image, you could use things, for example, like lava. They're quite successful, right? Lava, blip star, etc., and so on and so forth. You could do that. With certain degree of success, you could also do it with video. So I will put it like this. Video Llama, these two we are able to do. But if you do the opposite journey, what about this journey? To go from a text description to image, this was a slightly harder problem. And there are two sort of generations of models that were used. In the past, I covered vector quantized variational autoencoder and so forth. So the initial attempt was using a variation of that called DVA, like in which the quantization is not so hard, softer quantization. It was used to create, the initial version was, let me just call it generation 1, was with VAE based. By text grounding and then going back in reverse, it was a VAE based approach. But then on the scene came a class of models, quite interesting, quite revolutionary, and deriving from a part of physics. These were called the diffusion models. So let me just call Gen 2. And today, they all have their strengths and weaknesses. So for example, DALI, this is DALI. Today, you'll call it DALI 1, the first DALI. Its strength was that you could say, if you remember when DALI 1 came out, people were shocked because it's the first time they were seeing effective or plausible text to image generation. And the classic or the iconic of this DALI 1 was avocado shaped chair, right? Or daikon taking tutu on a walk or something like that, isn't it? Daikon. I forget what it was. Please correct me if one of you remember. What is tutu? Tutu the dog, isn't it? Or something to that effect. It was very effective, but its qualities it was more sort of a cartoonish, isn't it? The images that it generated, DALI, images that it generated were low resolution, right? And a bit cartoonish. Like sketch-like. It was pretty good at those things. Then came onto the scene a completely different way of approaching the problem. And this different way of approaching the problem starts with something that is worth discussing. And I'm going to do that. So when we come across the word diffusion is, one easy way to think about diffusion is take a beaker of water, pan of water, a glass of water, clear water. And if you happen to have some dye or some ink at home, perhaps you have a liquid food dye or something like that, just insert a drop here. You can do that. Or one easy thing that you probably do is you take coffee decoction, the coffee, and then you can pour concentrated milk or cream into it. And when you do pour that, you can see the diffusion process. What it means is this thing will eventually go and permeate in sufficient time. So suppose at T0, it will look like this. But by the time you go to T infinity, it will become a homogeneous, at equilibrium, the two things would have mixed completely, isn't it? So when you look at a drop here, it's localized in space. Geometrically, it has a well-defined structure, quantified structure. You can tell this is water, this is ink. Are we together? We can do that distinction. But when equilibrium is reached at T is infinity, then you can't tell. The ink and the water are all homogeneously mixed. Right? So completely permeated. The ink is permeated the whole water content. So now, this process is diffusion. What happens is at each time, if you were to look at discrete time periods, you would see a progressive dissolution of the ink drop into the water. Does that make sense? You have a progressive dissolution. Now comes an interesting question. Take this idea, and suppose we were to ask this question at each stage. So suppose you have this, and it looks like this at this particular stage, and there is some mixing up happening. You could ask this question, I'm at T, at the T is equal to N. Is there a way for me to understand what was the state Tn minus 1? You could possibly argue that you can do that. Why? Because from this, you can infer where it all came from. Right? You just have to take it and make it more condensed. So for example, this little bit, let me put it here, this little bit, it could not have come from here. It is very likely to have come from inside, isn't it? So there is a slightly differential probability where that bit of ink came from. You can create an ink gradient and infer that it came from a region of higher ink density than from a region of less ink density. Are we capturing the intuition? And therefore, that opens the door to asking the question, and this is a very interesting question. Therefore, can we infer the previous state? Assuming that Tn and Tn minus 1 are just very close apart in time, right? Let's say a millisecond apart. You can say, well, of course, I can. Diffusion is a slow process, and therefore I can undo it, because at each moment, I do have some notion of a gradient, and I could undo it. Are we together? And then you could say, can I go back and keep going back to previous and the previous and the previous state? Because if I can do it once, I could probably do it again. So you realize that as the diffusion is happening and you're moving backward and forward, two things are true. It is non-equilibrium dynamics. Right? The thermodynamic process is non-equilibrium. At equilibrium, you're lost. You have no idea what the original ink drop looked like or where was it placed in the beaker. Right? So you're playing with non-equilibrium states throughout. Then only you would have a gradient. At equilibrium, everything is lost. Are we making sense? Right? The other intuition that I want you to carry around is that if your steps are quite small, there is an inferential reversibility. See, thermodynamics won't allow you to reverse. Entropy only increases, right? you go from a state of less diffusion to a state of higher diffusion. But what we are saying is, by observing the diffusion state, tiny steps forward we can infer the previous state, right? Inferential. And that brings us to this question that let's look at an image and do something somewhat similar, right? What we will do is imagine that you have a picture. What would be a good picture?
Right. Is that like lip singing from an image? One is deriving that talking or walking, or if from an image person is walking.
Yes. We'll come to that. We'll come to that. How that is done. Actually, that is one of the papers we'll cover at some point. That's a magic thing that just came out, right? We will be doing that. But anyway, so think of an object that is pretty stark. Okay, let's make this kid's image. We all have had a childhood. We have all drawn this, isn't it?
On the right side.
What's that?
There was a small house.
Yeah, there was a small house here. Yes, so this is it. This is what we do. And then there's a chimney here. And then, of course, there has to be a tree somewhere. And a few birds flying here.
Yeah, there's some birds.
Right. So guys, here's the thing. Suppose I take this image. And from this, I take every pixel and I add a little bit of noise to it. I mean, whatever the pixel value is, suppose you have a value. So suppose I get a value. Let's take a number, 0.5. And I add a little bit of Gaussian. By the way, when I use the symbol, does it mean anything to you guys? What is this? A normal distribution. What it means is I take a bell curve centered at 0 with uniform distribution and I sample off it. Sampling off a normal distribution means what?
So what is the question? Sample?
A normal distribution. How do you sample off a normal distribution?
Normal.
Okay, I'll give you one way to sample off it. So how do you sample off a distribution? Sample off a normal distribution. Okay, there are better ways of doing it, but here's the basic intuition, guys. Do this. Just wrap it up. Can I wrap it up in an infinite box with this as a tippy tip? Right. With this, the tip of this. So here's your distribution.
So is it like within the first sigma, second sigma?
No, just bear with me. So you look at the y-axis. You're looking at the y-axis, guys. Now, y-axis goes from 0 to what is this? What will it go to? It happens to go to 1 over 2 pi square root. But you don't have to pay too much. 1/6. How much is 1/6? 18%. 0.18. 0.18 approximately. Okay. This is 1 over square root. Why? Because it's the nature of the bell. So something like that. So now, in this region, suppose I randomly pick a number between 0 and this. I can randomly pick a number. That much I know how to randomly pick. Right? So suppose you happen to have picked a number, this number. This number, suppose you happen to have. Right? Now, go either in the positive or negative direction. Flip a coin. Doesn't matter. You will hit something. Right? What is the X value here? Pick that value. You just sampled off this distribution. This is, by the way, this is for you to understand what it means. In reality, the way you do it is using smarter methods. You use something negative sampling techniques and other sampling techniques. There are many techniques to do that, but this is a way. Now, if you notice it in this region, do you notice that the values, most of the values that you'll end up picking are close to 0. Very few values will be far from 0, isn't it? To get to this value, you really have to hit close to y-axis, very, very close to 0 to get to a value bigger than this. So most of the time, you'll end up picking small values. So you take 0.5 plus this small, which has been sampled, and this is the notation. And guys, in preparation for the next course, which is more mathematical, can I use this notation? Is this now obvious what I'm doing? This symbol is the symbol for sampling. And what does sampling mean? What I just showed you. Pick from a distribution. You added it here. So now what will happen? Each pixel, if it was deep green, I just shook it a little bit. Now it is not so green. Okay. So this is called adding. This is Gaussian. Add a bit of Gaussian noise or normal noise. You added a bit of noise to it. So this picture will now get slightly grainy. A very tiny bit of graininess will show. And now I do this. I take this picture. Let me call this X0, the original picture. I go to X1, go to X2, and at each point, I'm adding what? Plus epsilon, plus epsilon, plus epsilon. And each epsilon is different. So epsilon 1, epsilon 2, epsilon 3, all of these are all sampled of normal distribution. And you don't have to add the whole amount. You can add very tiny bits of it, little Gaussian noises. So gradually, suppose I keep doing it till infinity. What is your X infinity going to look like? Because the sum total of all the perturbations will cause this to essentially the information to disappear. The noise, the Gaussian noise that you added would have overwhelmed the information there. You have no idea where it came from, isn't it? Of course, by infinity is a mathematical construct. In reality, it may be, let's say, 1,000 cycles. Make sense? Right? In practical terms, it will be 1,000. That's 1,000. You would have lost all things. But look at, so when now observe one more thing. What you have, this was E3. When you go to the E4, so this is X1, X2, X3. X3 depends on what? Does it at all depend on X0, X1? Has it been in any way affected by those? It is only derived from X2 and Gaussian noise. When something depends only on a previous state and nothing else, not on the previous to previous or the previous to previous to previous, any of those things,
Markov chain?
These things are called Markov chains.
I remember.
Yes. These are Markov chains. So if you have difficulty remembering Markov chain, here is a simple intuition for you to remember. When imagine that you're deeply inebriated. You have been visiting a pub, and you have been doing pub hopping. You went to a pub, it closed. Then you went to that other pub, right, which was supposedly through the back door in a secret word. What are those things called? There's a lovely word for it. Speakeasy. Yes. Oh, you know that. Right.
Speak easy.
Yes.
How do you?
Oh, even I know that. I've been to a speakeasy. No, because I've been to a speakeasy. Somebody took me there. Right? And I don't drink, but I enjoyed the atmosphere. But anyway, so then imagine that you went to a legit pub, and then you went to a speakeasy, and so on and so forth. And finally, you're walking back home. There is nobody who will take you for a ride home. So you're walking back home. You have no idea where you are. And so suppose you're at this place on the street. Your next position could be in any one direction, right? Right? But you realize that suppose you end up here now, your next position you have no sense of what you're doing. So you're following a Markov chain, isn't it? It could have been in any one direction, yeah, but you happen to follow a particular trajectory, which only depends on where you were last standing. Right? You could be stepping in any direction you want. That is a Markov chain. So one easy intuition you can carry in your mind is the drunken man's walk. The drunken man's. Yeah, drunken persons. Yeah, no, man, that is bad. Thanks for correcting me. Drunk. Let's say the drunks walk. Drunks walk. How about that? Drunkards walks. Yeah. So there you go. That's your intuition behind the Markov chain. No, you don't need to. You have no idea. I need to walk. Right? You have an intention to go home. You have no idea where is home. You just step forward and you think you're going there. So, yeah.
Sir, this Markov chain, that example X1, X2, X3, and E1, E2, E3. That E1, is it changing or?
No, every time you change. No. Every time you sample from the Gaussian and you add a little bit to it.
So E1, E2, everything is changing. So
everything
then how we can recover back to the
That's a good question, and we'll come to that. Yeah. See, yes, very good. So see, here's the thing, guys. If I make very small step, look at a drunken person. If the person makes very small step, you can at any moment have a certain radius of certainty that this person has come from these locations, within this location, isn't it? In the last step. Would you agree? Mm-hmm. In the same way, go back to this picture of the ink in the beaker. If the ink looks like this, let me just color the ink here. If the ink at this moment looks like this, and it thins out a little bit, what can you tell? By looking at the gradient of that ink, you can actually tell where you're coming from. What was the previous state of the diffusion? So when the steps are really tiny, the uncertainty of the previous state is limited. You can tell with a reasonable accuracy that of all the infinitely many states that the shape of the ink could have been, it is actually one of these very few perturbative states. Isn't it? That's the idea. So think of it like this. If I show you a picture of me and a picture of me with a little bit of Gaussian noise added to it, you would be pretty sure that no matter what, it is far more likely to be me, with just if I add a little bit of noise, than it is likely to be Tom Hanks. Isn't it? Was it?
6 shots later.
Yeah. 6 shots later.
Or like your 10th grade picture and current picture.
And current picture. So that's the thing. The band of uncertainty is limited at each little step. And therefore, that opens up the possibility that if it is limited, can the machine be trained to infer the previous state? You get that, right? Can I train a neural network So first think of it in abstract, in conceptually. Can I undo that? If human beings can do that thought experiment, surely machines can be trained to do that. Undo a little bit, isn't it? Right? And then undo a little bit, and undo a little bit, and keep undoing a little bit. But then when you undo, first, then we'll worry how to undo. You realize that when you're undoing, you're not predicting. It's a very subtle point that many people, I suppose, miss. You're not trying to predict what the picture, what the state of the ink was. That is inferred from your predicting what was the perturbation of that state. What was the noise that was added for you to be here? Right? So, in other words, if I am at state T, and I go, there's a epsilon sampled from a normal, with not just, so maybe there may even be a tiny coefficient sitting there, but let's do that. And you go to this state, xt plus 1. Right. I can train a neural network to pretty much infer. I may have certain loss of accuracy, exactly what happened. For example, the tiniest little speck on the cheek might go missing, right? But what it will do is it will infer the statistically most plausible state from which it could have come. Right? Do you realize that from a unique state, when you go to the next state and you retrain the network back, it is not trying to necessarily infer what it was here. It is trying to say what is the most likely state from which it came. And therefore, what it is trying to do is saying, what is that state? Because we know that xt plus 1 is equal to xt plus epsilon, the noise, right? What it is predicting is train a machine in the reverse direction, so the reverse becomes a reverse Markov chain, isn't it? A reverse Markov chain
One question, sorry. But before this neural net era, so we still had Markov chain last 40 years.
Yeah.
How did they figure out? If I recollect correctly, it is used in a lot of instrumentation. Right? I don't know, maybe wrong.
Yeah.
So
No, it is there. In different domains, there have been different techniques, but a lot of this has long history in physics. Right? So now what we are saying is train a network to predict. Suppose I give xt plus 1, and it could predict epsilon hat. Imagine a machine that can predict epsilon hat. Right? It can figure out what is the noise that was added. Then what can I do? I can do xt predicted. We are going in the backward direction. The predicted xt is xt plus 1 minus epsilon hat. Yeah. Does this make sense, guys? Hopefully. Obviously, that is it. So that is the game we play. Because we know something about epsilon hat. What is it? We have a pretty strong idea that it must have a Gaussian distribution. It has been sampled off that, right? So it must have a Gaussian distribution. So there we go. It's been taken off a Gaussian distribution. That is the clue. And now, do we know something that is very good at... Now, do you realize that the reverse process looks almost an act of denoising? Does that remind us of something? Autoencoders, and in particular, a special adaptation of autoencoder that we use with autoencoder plus residual links, skip links is called. What is an autoencoder with skip links called?
UNet.
UNet.
Yeah.
UNet. So you guys remember we did UNets. What was UNet? You would take an image and then you would go through the 3 channels RGB. And what would you do? you would do feature extraction at each stage of a CNN. What would you do with this, with the unit? You would keep on extracting feature maps. At the bottom, what would you get? A tiny feature maps, but lots of them. And then what would you do? You would go through a process of deconvolution, decon, and conv, and decon. Except that the extra thing you did, so this is basically your encoder decoder architecture. This is your Z state. The difference is you also do a skip connection. You sort of leak in the information, feature map. So when you're deconstructing this, let's say that you're deconstructing this state, what you're doing is you're taking in information that is going from here plus information that is coming from here. You know, the equivalent of this is this, right? And this is your skip connection plus skip frames. Both of these. Now, why would you do that on the image? So I'll just recap you in case you have forgotten your unit. Think about it this way, guys. The convolution is a journey from which an image which has a very high spatial information. Right? You know exactly where this dot is, where this nose is. But as you do feature extractions from it, higher representation learning, by the time you get to the bottom of it, the latent representation is semantically rich. It is saying cat or something like that. That's what it is saying, something like that. It has enough, but it is losing spatial. The trade-off is you lose spatial information in the convolutional states, but you gain semantic representations. Are we clear, guys? On the upswing, when you want to reconstruct the image for things like segmentation or super resolution, you know, denoising or creating blurry image to sharp images. Guys, we have done this blurry image to sharp images using UNet. Do you guys remember? We covered all this. Okay. Then what do? We not only want to go from semantic information to that, but if you want to sharpen that image, you also need to know which part. Where do I draw those whiskers? Isn't it? So therefore, that is what the purpose of the skip connection is. Because the skip connection is bringing you spatial information. Whereas this journey here, from the bottom up, is bringing you semantic information. And you need both to do a good reconstruction of the image. That is why UNet is very good at denoising, at super resolution. So this is denoising. Resolution, like if it is a blurry image, you can sharpen it, and it is very good at image segmentation. Are we together, guys? All of these tasks, it is good at that. So now what can we do? One second, I'll come to that, Patrick. So guys, do you realize, can we use that here? If UNet architecture is a good denoiser, hey, that gives us a reverse Markov chain, isn't it? So what can we do? Theoretically, and there's more to it. So I'm building the ideas systematically. I can take a blurry image, xt, and I can get to xt minus 1 to a UMAP, isn't it? And then I can do this again, UMAP. And I can keep doing that till I get to x0, and I claim this is the picture you came up. This was the picture, right? Are you seeing that? Of course, now the whole question is, now, wait a minute. Are you kidding? If I have complete random noise, how can you ever know whether it was a cat or a dog or a house? So we need some way to direct the denoising process. Do you agree? We need some way to denoise, because if you go to the limit and all you're looking at is random noise, it could produce anything. We need to think through that. So we'll come to that. Patrick, your question.
So I think this idea of this is similar to like how your transformer architecture, there's also like.
Yeah, exactly. It's the same thing, residual. The idea is residual. I believe that is one of the less appreciated aspects of neural networks. And effectively, today you almost never make any neural architecture without residuals. Yeah? This is nothing but encoder decoder, right? A DC GAN, DC like autoencoder with just this thrown in. Right? Okay. So now, guys, at least we are building up the pieces now. Right? Now comes an interesting thought. We still need to do the text grounding. Where's the text? I want a cat. Right? I have a text to do that. How would we do that? The first architecture that came out was Glide. What you did is you take an image, you do again the same journey. You take an image, very much like Clip. It's very reminiscent of Clip, and in fact uses Clip. What you would do is you take this and you have a caption to it, right? A cat, or enough of cats. Here's a cow jumping over the moon. Here's the moon, and here's a happy cow. Right? Cow. Here you go. And so what you do is, now this is text. What we can do is we can encode the text, pass it through a, for example, think what happens if you pass it through a transformer encoder. What would you get? You would get the tokens with a CLS token also. Does it remind you of something, guys? This is plain BERT, right? BERT-like thinking, BERT and its encoder. You pass this. Now you take this image, and what you do is you concatenate this information to this image somehow. How you do, we come to it. The other thing you do is when you implement this unit, you make it attention-based unit. In other words, you use attention network. The difference is the original unit was pure CNN, right? See, convolution decon. But nowadays you do attention enhanced or attention based units. So attention, now what happens is you get representation from the image, you get representation from the text tokens. Both of these you pass down, right? And you train this network. Now what happens? When the attention thing comes, this image is paying attention to each of the tokens, text tokens all the time. And therefore, the next state of the image is conditioned on the text token. What does it mean? When you reverse diffusion it, you can leverage the same text conditioning to direct the backward journey, so long as you have a text available to you. Right? Because it knows that what noise step, how will the noise addition be conditioned on this text? Are we together? Right? And so what we are basically saying is, and when you do this, there is a problem though. So this is it. You train the network using this. Then you use a couple of tricks actually. What you do is, see, you can, when you're reversing it, you could play a couple of games. One is our old familiar clip architecture, clip. You can bring it to your service. What you can do is, suppose you're going from xt plus 1 to xt. You're trying to go back because you're sitting on noise. You're trying to go back, or let me do that. Let me just write it in this way. This is reverse diffusion. So when I go in this direction, it means I'm going from noise to image. Are we together? So what we can do is I can go from an image, let me just call it xt plus 1 only, and I'm going to xt, like, or rather t. Now here I will use, I shouldn't use the word. I hope I don't confuse people when I say I'm going to a cleaner image, right? Noisier, denoise. This is a denoise journey. Now what happens is I could go, I have the caption available, right? Now what can I do? I let this journey through UMAP go through in between. Then I have this image. What I can do is I can take the image and I can pass it through an encoder, right? Clip encoder, pass it through a clip to get the vector for t plus 1, image vector for t plus 1, isn't it? At the same time, there is one thing that is constant, right? And so what can I do? I can look at the gap between vt plus 1 and v caption, this, and I can ask this question. This p plus 1 state, the vector, depends on the parameters of the model. It is conditioned on whatever neural network I have. So everything is being conditioned on some parameters of the model that I'm training, isn't it? What can I do? I can say, hey, change the parameters in such a way that it will minimize the gap between these two. Bring them closer. What the caption is trying to say and what the image you reproduce. So suddenly, if from you begin to believe that this is not a cow, but it's a giraffe, this bit of learning will pull you back. This last term will start pulling you back. Does that make sense? Because the caption is the one, is the magnet, is sort of the grounding gravitational force that's continuously pulling the image, the so-called better image, to be in the right direction.
Is this coding that it's the caption that's leaking in the UMAP, or the one that's creating that's part of the stick collection in the UMAP, or
No.
just assuming that
Yeah,
the caption gets leads into the reconvolution or the reconstruction?
Yeah. So what you do is you let this happen. So all of this, so there's a multi-step. These captions, they induce this whole UMAP journey. So they are part of the UMAP journey. But even in the UMAP journey, you came up with a better image. But then you use clip on the caption again, and you use this argument. You said, okay, even though you were caption informed, I can still tell how off you were from the caption, how off your image is from the caption. And that would be this. I can use that to learn and change the parameters of the model in such a way that you make less mistake.
Sure, I got that part. The part I was worried about was the attention guidance through the whole UMAP, because you said it was stick collection.
Oh, yeah.
That coded into the article.
Yeah, it's all coded into. And so one of the things we should do, guys, I highly encourage it. Literally the video that you pointed me to, the 5-hour video, very well it explains in the code that you'll see, you will see that. See, today we don't do architectures without residues. So it's sort of a big thing. So are we together? This is method one. This is one trick they use to, now you realize that you can really get much more crisp image because you're guiding it with text using clip, right? But there is yet another trick in the bag. There is a method one, there's a method two, and we are talking about the glide. By the way, we are talking about the glide paper, very specific paper, glide paper. In the method number two, what you do is something a little bit smarter. What you say is, okay, let's do this. We know when we are training, let's do this. Let me draw the picture. I start with x0, goes to x1 to xt, t plus 1. Are we together? This is it. Let's say that we are sitting at xt plus 1 and we are trying to, when we are going in the forward journey, we have gone. We remember, we do have access to xt. The ground truth we know. And so when you're doing the reverse, what you're producing is not xt. You are actually producing xt hat, your prediction of the model, right? It produces the reverse journey, produces from this. Well, actually, even this is technically a prediction from a previous step, but let's say from xt hat, t plus 1, you're predicting the xt hat. So far, good. But you happen to know xt. So what can you do? You can go pass, now you have the ground truth, so-called ground truth at t, that is xt. I can pass it into a VIT encoder. And what will I get? VT, the ground truth VT. And I can take X, by the way, I can take xt plus 1, this prediction, xt prediction. And what can I get? The predicted vector, encoded vector. Right? Now, let us say that VT is here. Ground truth vector is here. You predicted a vector here. Right? You know that even the ground truth is a bit noisy. Right? Though now, and by the way, you have included the, hang on, let me get this right. Am I getting this right? Oh no, you don't. You have the xt. You have the predicted word. Now this comes from the text. Actually, I apologize. This is from the text.
That is method 1, right? You are talking method 2 now. So
Yeah, I'm talking method 2.
Right? That also needs text.
Yeah. So what you do is you take this direction. This is the text, and you overshoot a little bit. Right? In the direction of the text, you can overshoot from your prediction. You're saying, I needed to go in that direction, right? Let me overshoot and go some more. Right? And this will be VT, very texting direction. Right? You pick that. So you say, you know, there are couple of methods, and I hope I didn't make a mistake. It's been a while since I read this paper, but yes, I'm pretty sure I got this right. All right. So read the paper and correct me if I'm off in method 2. So what you do is there are these 2 techniques, and when people use this, right off this paper, I believe Glide came out of Meta. It showed that the results were pretty good. Not Meta, sorry. Was it Meta or OpenAI? I think I forget. OpenAI. One of you can look it up. It's on the course portal now.
But yes, fundamentally the way I'm understanding is with the help of text.
With the help of text, you're continuously doing that, and you realize that so long as the text is directing you, it sort of helps you denoise. So see, it just helps you follow a very well-directed Markov path. Right? It is not just undirected random walk. So it is almost like only a partially drunk. You skip easy. So you get back to it. Then came a stable diffusion, which brought in one more innovation. What did stable diffusion do? What it said is that, see, when you do this, you're dealing with very small pixel, like you're dealing with all of the stable diffusion you're doing in the image space. I mean, sorry, diffusion you're doing in the image with images. Are we together? Mm-hmm. And images are computationally brutal. You can do with like 500 pixels or 256 pixels or something. You can't produce high resolution. It is computationally too brutal, because how many steps of denoising you do typically to produce an image from noise from a text? Typically, it's at least 500 steps or 1,000 steps. Mm-hmm. So at every step you have the UMAP, every step you have this loss function, every step you're doing all of that. Lot of computation. So an alternative, what Stable Diffusion brought about this algorithm is a dead obvious idea in hindsight, but blinding is brilliant. And as all brilliant ideas are, the moment you see it, you say, of course, that's the right way to do it, kind of thing. Right? A very good idea. What it said is that, see, guys, let's not do stable diffusion and this whole diffusion back and forth training in the picture space. Let's do it in the latent space. Remember, we say that the whole point of representation learning is to find the best representation of that information, of the input. So what is a good information extractor? Autoencoder, right? So what you do is you first put a encoder. So here is your X naught. It goes in to produce your Z naught, a latent representation, right? Then you do all of this back and forth Markov chain for training, right? With text grounding and everything. You play this game in this space, and then you have a decoder from a latent state to the image. Does it make sense, guys? Right? If you do this, right, you only work in the latent space, and at the last moment, you do that. Then you're in a very good state because you can take a fairly high resolution image, right, encode it down to a lower dimension, and work with the latent representations. Do that, and then super resolution it back up. Right?
Cool idea.
Yeah, cool idea, right? And if you want to super resolution a bit more, then what prevents you from putting another UMAP or something like that to even super resolution that, right? And so that was stable diffusion. And when stable diffusion came out, you saw obviously the good part of stable diffusion was, the main point of stable diffusion was, see, up to this, look at glide and all of that. You're comfortably in the image space, which is big, computationally brutal.
Yeah.
You open your eyes thinking, yes, yes, yes. You need our hardware to do it, right? Run on big servers. And then comes stable diffusion, and it says, hey, if you work in the latent space, your little 3090s, 3080s, 4060s, 4080s, 4090s, your consumer grade hardware, this is the domain. This entire thing is the domain of consumer grade hardware. And so suddenly you could do diffusion models on your workstations rather than making API calls.
But doesn't that mean that like the encoder needs to be really good if you want to work in the latent space?
That is right. That is right. And that is why the stable diffusion models, right? By the time you train, I mean, you don't want to, like, it's hard.
Did they train the stable diffusion models and the outputs of it? Because if that's the case, then you need to have those three steps in order to use it.
Did they train on the output? See, no, because it is text to vision, right? All you need is human labelers to tell how good it was or something.
Well, yeah, but at the same time, now that we have stable diffusion, we can make an even more rich latent space because then we can send everything to latent space because it's a shared space between the image and that.
That's right. So one way to look at it is all that stable diffusion did is had the smarts to realize that, hey, do whatever you want to do in between, but put an encoder decoder here and work on the latent representation, not on the original.
Is there any work there? This is kind of an unrelated question, but is there any work being done to find the orientation in the latent space, like in terms of which dimensionalities relate to particular like labels that exist in humans?
That work is there. So people have found that whenever you do the encoding of images into this, they're usually, after all is said and done, because of the text grounding, they show semantic properties.
Mm-hmm.
Because
so that was part of my question. So the text binding is happening in the latent space, right?
Yes. Yeah, text direction is happening.
How is it?
So as far as the machine is concerned, so think about it. Imagine that glide is sitting in there.
Yeah.
As far as the glide is concerned, what it is seeing is a latent space image and text. It goes about its business. How does it even know?
Also, text is also in latent space.
Text is always, because the moment you pass it through an encoder, you get the token embeddings.
Oh.
That's that. As simple. So guys, that is stable diffusion. Now, if you look at these ideas, I hope you realize that none of these ideas are, I hope you understood those ideas. I didn't go into the mathematics of it too much. And in fact, I might have gotten you guys a little bit astray. Go back and look the method to how it works. Confirm with the specific details of the idea. It doesn't matter. In broad strokes, I hope you understand what diffusion models are. Okay? Now, as a task, please go read the 3 papers. I put just 4 papers there. The 4th one is optional. Like you can do even better than this. You can go even higher resolution with the stable diffusion model. But the main point is stable diffusion does diffusion in the latent space. Okay? That's why these are often also called latent diffusion models. So LDMs. With this being there, observe how the entire journey is based on simple ideas of diffusion, non-equilibrium thermodynamics. Right? And just the fact that you can see what you're predicting is the noise that you can subtract out. Now, one more thing I must mention, this is a subtle detail, but again, technical detail. One of the things they found is, suppose you are trying to go from xt plus 1, reverse diffusion, this is the reverse diffusion, to xt. You're trying to predict the xt state. Huh? Then suppose what you're really predicting is the epsilon, isn't it? You're predicting the epsilon. When you get the epsilon, don't be greedy. Don't immediately do. So I misled you by saying xt hat is xt plus 1 minus epsilon. This is what I said. And now I make a correction. It is not that. It is actually, you take only a little bit, maybe half, maybe 1/5. Remove a little bit of the noise. Don't get completely careful. Because remember, your noise prediction may not be very accurate. Right? So take a little bit of the noise out, not completely. And this is the correction that I will make in the beginning. I don't think yes. So when you do this, where am I? I must have written that equation somewhere. Oh, it seems I didn't write that equation. I wanted to. Oh, yeah, here. So what you do is this one needs a bit of correction. You can take a little bit of noise, a small bit. This is somewhat like the learning, the learning rate. When you know the gradient, you don't just hop the full magnitude of the gradient during weight update. You take a little learning step. It is in the same flavor. And so those are diffusion models. What can you do for now? This diffusion model, the big thing that has happened recently is people have created purely transformer-based diffusion models. So remember this one I brought in CNN, UNet, etc. Now UNet itself you can do with attention, right, and so forth. Recently there has been a lot of progress. Time permitting, I don't know. Last session I want to keep just to summarize everything we have learned the final day and hand out your certificate. So I don't want to teach anything new. But how about this? In one of the subsequent Wednesday paper readings, I go over all of these things like the Sora. How many of you are interested in the Sora architecture? Sora paper or so forth. And video generation and audio generation and so forth. So enough of you are. On the remote, no one seems interested, or maybe people have disappeared. Oh. Like in the Wednesday paper reading, I'll cover the Sora paper, Sora articles and things like that. And video, all the video diffusion models and so forth. The EMU. And then the whole, obviously, the alternative to all of this is, at some point I may compare it to the JPA way of thinking about it and so forth. So those things are for future, guys. With this, I would like to end today's, I got one hands raised in Zoom. Nice, thank you. And yeah, I got you. Go ahead.
Oh, Well, this is maybe a less reading section in of itself, but like, how does this compare to the normalizing flows of these?
Normalizing flows, great point. So see, normalizing flows have a more specific structure. See, suppose you have xt, you go to xt plus 1, you don't introduce noise. You say that this is f, there's a function that the network emulates, so that the machine has to learn f inverse of xt.
So this is like a reflection of that approach we assume that this is sort of PDB involved, and then you are going to
Yes, it's a more thing. It is pretty much normalized flow. You basically say that I need invertible functions.
Not using the error, not using the
Yeah.
loss, but reverse function.
Inverse function.
It's just a model.
Yes.
Yeah.
It's just the function seems that it's completely random.
Yeah. Normalized flow, by the way, I don't want to speak too much about it because it will be part of that summer school. Those of you, see, it gets mathsy. I'm already talking math, so let's not do that here. Any questions, guys?
Yeah, Asif, I have a question there. Can you scroll up to the unit diagram you have on the? So I'm trying to. So in this, I'm not quite clear as to where diffusion is happening in the unit model. So you're basically getting feature map extraction, whereas the xt minus 1 in the context of unit.
Oh, no. Okay, so let me go back. The classic unit has nothing to do with diffusion. Classic unit is a conv, deconv with skip connections, right? And when you deconv, you can basically what you're doing is in the deconv journey, upscaling journey, I can use both the semantic information coming from the deconv process and the spatial information coming from the skip connection. And that can help me do the three things: denoising, super resolution, image segmentation. Now, so that is unit completely. And now comes this world. You think that you have a grainy image, right? Now, we use the denoising feature of the unit. Remember, units can denoise. So I use the denoising feature of unit to do the back thing. But when I do the back thing, the hint is that I can do that. But I cannot do that if I start with complete noise. Right? See, what happens with these diffusion models is, in reality, all the input is just text. Output is image, isn't it? So input is complete noise. Like there is no image to begin with. You can just sample off a Gaussian noise and shape it into the shape of a picture, and it is total noise. So what is the role of UMAP? UMAP is not going to be able to produce anything sensible by just denoising noise because it doesn't know what to produce. There's nothing there, right? UMAP works only if there is some signal present. It will sharpen the signal, right? It will try to denoise it. But when the signal itself is not there, you can't. So then it leaves us with only one problem, one task to do. We need to train a unit that is text grounded. Right? So we need a new architecture for unit, a unit amplified with attention. So you need a new architecture, unit plus attention, and it uses, and again, I've glossed over some of the technical details because we'll cover it later in the summer course. It uses actually global attention. And the global attention is a cross attention between image and the word tokens. Right? So, which is why I drew this. And by the way, this is not at all, when you read the paper, it's not so obvious that that's what they are doing. You have to look at the code. And that is why the video that I posted on the course portal, it's actually one of the longest videos you can imagine. It's a 5-hour video. In 5 hours, it literally, line by line, you can code the entire diffusion process. And that code is on GitHub. And when you look at that carefully and you watch that video, which is very interesting, who's the author? I forgot. Patrick, who's that? The author of that video, that diffusion, reverse diffusion video. Umar Jamal, yeah. So
Yeah.
that video is really very good. And when you see that, you realize that what they are doing is they have the UMAP has been amplified with attention, and this attention is the one that forces image tokens to pay attention to text. So what in reverse it means is that when you are going from a noise, the only thing you have available to you in the beginning, in the very beginning, you sampled off a noise, you have nothing. The only thing you have is the text tokens. And so the denoising process is getting guided by the text, right?
Yeah,
So
yeah.
let me put it this way. Suppose you denoise, the UMAP denoises, this was pure Gaussian, right? So
Yeah.
let me just say this was just Gaussian. And it could produce a spectrum of images, image, let's say I1 to IK. But now what I can do is, because you can compare it to the text vector, you can look at the gap between these two, the encoding of this image and this text vector. And by doing a gradient on that, for example, the difference, you could say that, no, this is better. And I want the neural network because ultimately this is just made up of theta that is doing all of this. Right? You basically say, I want that value of theta, optimal theta, that produces, that denoises it, given the text in such a way, right, that it's
Yeah,
closer.
yeah.
That's a basic idea.
So I think just one follow-up, sorry for kind of staying
Yeah.
on that. So
Yeah.
like the way I understand the use cases for diffusion is, say for inpainting, I have a lawn and I'm inpainting some animal in the lawn. So where is the noise involved there?
No, you are imitating. No, please say that again.
So say I have a lawn and I'm inpainting a dog in the lawn.
Okay.
That will be a diffusion model. So where is the noise part there?
Oh, yeah, that gets the in painting is slightly more interesting. Think about it this way. So suppose you give it a lawn. All you see is green grass
Yeah.
growing, right? Lawn. And now you say that a dog in the lawn. Now what happens is the encoding of this, think about this, the encoding of this image vector and this text vector, there would be a substantial gradient between these two, right? So if the machine is like, this is all at inference time, what happens is that it will basically say, if this is X naught, I need to produce a X1 whose encoding, embedding E1 is closer to the embedding of this text, let us say VT. And then I need to produce X2, which gets even closer. I need to produce a X3, which gets even closer. And finally, when I'm done, I have a XN, which now has a dog sitting in the lawn.
I see. Okay.
Right? Because you literally say that you're not rebuilding from noise, but you're just saying, I'm going to a more error state to a less error state.
Yeah. Okay.
And that is it. And gradually a dog appears into the picture.
Thanks.
Or another way to put it is that in pure, like when you generate images from zero, of course you start with noise. But when you have a picture onto which you want to put something, you treat that picture as though it was the original noise. And you then make deviations on it till it comes closer and closer to the text ground.
Okay. That's what I was missing. Okay. I got it. Yeah.
Asif, at some point you will cover the GNNs, right?
I'll cover the graph neural networks. Well, yes, it's got pushed out because of, we ran out of sessions, 12 days. I apologize that we ran out of GNN. I want to cover GNNs definitely. By the way, how many people are interested in GNNs? One of the things is that the moment I say GNN, like 3 hands will show up at most. Okay, at this moment, literally validating what I said, there are only 3 hands. Look at Zoom. 4 hands. Okay. So, and Sheila here is raising her hand. So, yeah, I'm going to definitely do. See, with GNNs is something very close. If somebody were to ask what are the most important topics in machine learning at this moment, going forward, the areas of greatest breakthroughs, GNN is at the top of that. Yet, when I ask people, how many of you want to learn GNNs? Very few people even are interested. And here's the situation, and I'll just stop the recording now.